All right. Okay, so I'm going to talk to you about two different things today. I'm going to talk to you about end behavior, number one, and finding holes, although I already kind of taught this to you already. But we'll go over it, nail it down, make sure we got it for sure. Okay, so end behavior. First thing you need to do is put your phone away and look up. There you go. Perfect. Okay, so I'm going to go backwards just a little bit. Okay, and talk about some of the functions that we did before. Okay, so x squared is this beautiful little parabola. Okay, so the end behavior is basically where these little arrows are going to. Okay, so if I go to the right, as x approaches infinity, what is my y value approaching? Infinity. Okay, so the notation for that, and I'm going to write this on the side, is as x approaches infinity, the f of x, which is the fancy name for y, approaches positive infinity. Okay? The left end over here is as x approaches negative infinity, what's my y value doing? It's going to positive infinity. Good. So there is the notation for end behavior. See that? Looks pretty complicated. Okay, so let's look at this one. This time we got an upside down. Okay, so as x approaches positive infinity, the f of x is approaching. Very good. Holy cow, you guys are getting this way better than last class. What's my left side doing? As x approaches negative infinity, what's my y doing? Negative. Oh, yeah. You were just raising your hand, right?
Exactly.
There you go. Good. Okay. What about a John Travolta? Okay. So as x approaches positive infinity, what's my y doing?
Positive.
Going up. F of x goes to positive. Okay. As x approaches negative infinity, what's my y doing?
Negative.
Going down. Nailed it. You guys got this. Everybody okay? Ooh, that was a bad infinity. There we go. Okay. So I'm going to skip that one because I think we understand at this point. Let's talk about rational functions. Oh gosh. Okay. So the first thing that I'm going to do is I'm going to go over what I did in the last assignment, okay, and I'm going to graph this. Okay, so first of all, do I have a horizontal asymptote? Yes. Where is my horizontal asymptote? Is it bigger on top, bigger on bottom, or is it the same? Same. So therefore, the number in front, 3.
Where did you get 4?
Oh. 3. Okay, my vertical asymptote comes from where? The bottom. Okay, so what value makes the bottom 0? 2. So we got a vertical one at x equals 2. I can find my x-intercept real quick here. What am I looking at to find my x-intercept? Just the first part of that. Just the top. Okay, so what value makes the top 0? So if I set that equal to 0, if I set that equal to 0, I could like minus 1 and divide by 3. Good. Negative 1/3. Can I find my y-intercept? How do you find the y-intercept?
Plug 0.
Plug 0 into the x. Oh, that's easy.
Negative 1/2.
Negative 1/2. Good. All right, so let's draw this. So I got a horizontal asymptote at 3. 1, 2, 3. Vertical one at 2. An x-intercept at negative 1/3. I'm going to call that right about there. Y-intercept at negative 1/2. Oh, that's just exactly right there. What does this look like? Should we use Desmos? Let's use Desmos. I like Desmos. It's like my favorite. I love Desmos. Okay, let's type it in. Let's get rid of that one. So we have on the top we had, what was it, 3x plus 1, right?
Yeah.
And then the bottom was x minus 2. Yeah, I think you're right. Okay, so check this out. So we see the very familiar hourglass function, right?
Decimals have a like an
Yeah, it does. Yep. What's the end behavior of this, you guys?
Oh,
This. Check the. Okay, so I'm gonna go back into Desmos and like zoom way out, because remember the idea, end behavior is as x is going to infinity. So we're looking way out here and we even further beyond. So I'm gonna touch on the line. Can you guys see that? So my x is a big number and my y is like 3.058.
It's approaching 0.
You think so?
Or is it
Let's
approaching
go
negative?
even further out. Let's go way over here. Now it's at 3.01. What is it approaching?
3.
It's approaching 3. See, it's at 3.0. Watch, keep going.
Yeah, what was it?
Oh, we'll just go to a million. Let's go way over here. Look at that.
It just stops at 3.
Because it can't go past 3.
Yeah, now it's like Desmos is like, dude, I can't go any smaller than that. I'm gonna call them that 3. It's really like 3.000001.
So if you use it out,
Keep going. You still don't believe it's 3?
I
Okay, Desmos, you can do it. What do you feel? Does that pretty good? I think it's getting closer.
Yeah.
Because it can't go past 3. Right?
Right. Exactly. Okay, so the whole idea of an asymptote is that the function is getting infinitely close to it. It's never going to cross it. Okay, in the end, it's going to get infinitely close to 3. Okay, so the end behavior for this function, as x approaches infinity, where is the y going? It's going to 3. So if we go the other direction, oh my gosh, I don't know if I can zoom out that. Oh, there we go. And go to negative infinity, go to the left way over here. What do you think this one's going to approach?
3.
3. It's exactly where the horizontal asymptote is. Trey, put the phone away. If I have to ask you again, I'm going to take it.
Hey, you're not in your corporate.
What we get, sorry.
Okay, so does anybody have like a resolution to tell me about end behavior? Observation? Like where could we maybe come up with a 3 if we had no Desmos?
The asymptote, the horizontal asymptote.
From the horizontal asymptote. Horizontal asymptote tells us about the end behavior. Okay, so let's do question number 4. Let's see. Okay, so let's check out number 4. I'll do this one in green since I kind of overstepped my boundaries here. Okay, let's start with my horizontal asymptote. How do I figure out my horizontal asymptote in this one?
Bottom.
It's bigger on bottom. So how did you know it was bigger on bottom?
It's back.
Okay, so remember you have to be thinking this if this was in standard form, right? So if I FOILed this out and I would have x squared on the bottom, I would have x over x squared, so it's a bigger on bottom. So if it's bigger on the bottom, where's my horizontal asymptote? 0. Okay, where are my 2 vertical asymptotes?
2 and negative.
Good, 2 and negative 3. I'm gonna go ahead and just stop there and go ahead and graph this from that. have vertical at 2 and -3. And go ahead and type this into my Desmos. So we had x divided by, what was it, x minus, what did I have?
X minus 2.
Minus 2,
X plus 3.
x plus 3, thank you. Okay, so obviously we can't see anything because I'm so zoomed out. And I forgot to wake the function up. How come it's not turning on? Where are you? Oh, it is on. It's just so close. It's not graphing it. Let's see. There we go. There it is. Okay, so check out this one. This is kind of an interesting scenario. Okay, so you have that hourglass, but in the middle of the two hourglasses, there's a John Travolta. Okay, which that would be kind of hard to predict without something like Desmos. There's ways. Yeah. So what's my end behavior?
As it approaches zero.
0, right? 0 in both directions, right? Okay, so one thing I want you guys to notice on this particular function, let me draw it out. Okay, so as x approaches infinity, f of x approaches 0. As x approaches negative infinity, our y approaches 0. Okay, so did anybody notice that it crossed the horizontal asymptote? Okay, so here's something different between a horizontal asymptote and a vertical asymptote. A vertical asymptote you cannot cross through because it's that golden rule of can't divide by 0. But the horizontal asymptote you can cross, it only tells you about the end behavior of the graph. Okay? So you can cross the horizontal asymptote. Okay, let's do one more because this is kind of an interesting scenario here. All right, first of all, horizontal asymptote. Bigger on top, bigger on bottom, same? Okay, so what happens if it's bigger on the top? No. There is no, and there's a slant. Okay, so here's a scenario where we have no horizontal asymptote, and there is a slant. Okay, where is my vertical asymptote? Okay, good, at x equals 1. Okay, so check this one out. This is very interesting. So we had x squared, was it minus? Minus 5x plus 6. Minus 5x plus 6. Divided by x minus 1, right?
Yeah.
Okay, so check that out. So you still see that like hourglass effect, but instead of leveling out, the end behavior is going where? Where is the right end going? Up. Yeah, to positive infinity. Okay, so slant asymptotes are going to go up to positive infinity or possibly down to negative infinity. You'll have to graph them to see. Okay, so I would say for this one, as x approaches infinity, my f of x goes to positive infinity. And as x approaches negative infinity, my y goes to negative infinity. Okay. You guys feel like you have this, or should I do one more? One more? Okay, one more. Okay, so for number 6, can you guys see over the top of that, it says 4x minus 1. Here, let me erase that little. 4x, oh, yeah, 4x squared. Yeah, let's sort of 4x squared. Okay, so is this going to be bigger on top, bigger on bottom, or same? Same, so horizontal asymptote at 4. Remember when, yeah, same, exactly. Okay, to figure out my vertical asymptotes, I need to factor this. So what does the bottom factor into? So what two numbers multiply to -2 and add a +1?
-1.
Multiplies the 2. There you go. So vertical asymptotes? 1 and -2. So do I need to graph this for you to tell me where my end behavior is? Can you tell me where it goes? Yeah, exactly. I only need to know the horizontal asymptote to know about the end behavior. Okay? Yeah, if you don't need to, if you know where the horizontal asymptote is, then you can just tell me what the end behavior is. It's going to 4. End behavior. Awesome? So we good there? Oh, let's talk about holes. Yeah. Part 2. Finding the holes. Okay, so on this example, basically what I'm going to do is just kind of do everything. Okay, so I want you to be able to graph this function. You need to be able to find the asymptotes. You need to be able to find holes. You need to understand what the domain is. The end behavior, which we just talked about, in points of discontinuity. They will talk about that. That's very simple. I'll talk to you about it after I graph this. Okay. Horizontal asymptotes. Where is my horizontal asymptote? Is it bigger on top, bigger on bottom? Same.
Same.
Same, so therefore?
0.
What?
1. I was just trying to go from there.
Okay, so the next thing that I'm going to do is I am now going to factor it because I want to figure out where I could possibly have holes and I could possibly have vertical asymptotes. And the only way to figure that out is to factor the top and factor the bottom. Okay, so what does the top factor into? What two numbers multiplied it? Okay, 2 and -1. Yeah, you got that one. Okay. Oh, okay, so -3 and +2. Good. Okay, so now if I look at this, does anything cancel?
Yes.
Yeah, what do you have on the top and on the bottom? The x plus 2. Okay, so when something cancels, what is created?
Hole.
The hole. Okay, so we have a hole at what x value? At -2. Okay, do you guys see? All I have to do is figure out what value makes that 0. Now, can I figure out the corresponding y value? How do I find the corresponding y value?
Plug it in.
Okay, good. I plug it into the simplified version. Can we do this mentally? So -2, ignore the canceled part. So I have -2 minus 1, -3, and then -2 minus 3, -5. So I have -3 over -5. 3/5. Good. Okay. So now I have a vertical asymptote left. Where is my vertical asymptote? Look at the bottom. 3. Okay, so vertical asymptote comes from what's left over that does not simplify on the bottom. Let's do intercepts because those are valuable. What's my x-intercept? Where am I looking for x-intercepts? Top, good. And I'm only looking at the one that's left. Okay, good. X-intercept at 1. What about my y-intercept? How do I find the y-intercept?
Is that -1 over -3? Or is it just top?
Yeah, that's fine. So I'm plugging 0 in, and I can use my simplified version, or I can go back to the original. They both give me the same answer. I have -1 over -3, which is 1/3, Or I can go here and get negative 2 over negative 6, which is also 1/3. So I have a y-intercept at 1/3. Did we get everything? Oh, end behavior. What's my end behavior?
1.
1 on both ends, right? So as x approaches infinity, my y approaches 1. Ditto on the backside. I feel like that's such a long notation, just for telling us it's 1.
Why do we use that instead of y?
What's that?
Why do we use that instead of y?
Because technically our function is in terms of f of x instead of y. All right, here we go. So we're going to graph all this information. I have a horizontal asymptote at 1, so I'm going to draw that as a dotted line. I'm going to go to my vertical asymptote at 3. I have a hole at negative 2 and 3/5. Let's see, negative 2. So it's going to be just slightly above. So a hole is just like a, you guys know what a hole looks like, right? Hole. That's a hole. Perfect. Okay, x-intercept is at 1, so that's a solid circle. Y-intercept is at 1/3. Oh my gosh. Just barely. So, do I need Desmos to graph this?
No. Just to make sure.
If you want, absolutely. It's not against the law to use Desmos. But can we make a prediction of what this looks like without Desmos? What does it look like? Exactly. It's your hourglass. When there's one vertical asymptote, it creates that hourglass. You got to try to make it go through the hole. Okay. Oh, I forgot to talk about domain and points of discontinuity. Okay, so my domain, the domain is going to come from the values that x cannot be. There are 2 of them. What are the 2 values that x cannot be?
-3.
Close. +3 and no.
Negative.
No. So remember, values that x cannot be are values that we cannot divide by 0 with. So what values make the denominator 0 at any point before canceling? So what would make this denominator 0? 3. What would make that denominator 0?
-2.
-2. So I'm going to write this as x cannot be 3 or -2. And the points of discontinuity, do you guys understand what points of discontinuity? Have you heard that term before? Continuity? Okay, so a function that is continuous is a function that I can draw without lifting up my pencil. So that means there's no holes in it, there's no breaks, there's no jumps. This one has 2 points of discontinuity. Where are the 2 points of discontinuity? -2 and 3. Exactly. So the domain is giving you the points of discontinuity, the places where the function doesn't exist and it breaks apart technically. Technically, if I drew this, I would have to lift my pencil and go to the other side of this hole to start drawing this again. And then I have to lift my pencil up here to continue drawing that right side. Why is there a hole? So the reason there's a hole is because since we have a hole at -2, if I go back to the original function and plug -2 in, let's do that and see what happens. You get, okay, that was the fast version of that. Yeah, you get 0 divided by 0. Okay, which is a problem because you cannot divide by 0. And that's why there's a hole. If you get a 0 over 0, that's where holes are. Okay. So points of discontinuity, we'll say P of D, points of discontinuity, x equals 3 and -2. Those are completely related. So what do you guys think? Shall I do one more of these?
So like the domain is where
Think you got
points
this?
can't exist.
Right.
X can't
Exactly.
exist.
They can't exist there. That makes the function undefined. So are we good? Do I need to do another example?
How did you get 3/5 for the?
Oh, 3/5, I plug -2 into the simplified form of this. And just so you guys know, on the worksheet, if they ask you for a whole, if you can find the y value, that's helpful, but I definitely want you to give me the x value. Okay, so I'm going to say optional to give me y. If you can find it, do it. If not, I'm not going to get all upset about it. So we good?
Yes.
Worksheet, yeah, let's do the